Hello and welcome to section 10.3. Today's topic, we're still on vectors and it's going to be the dot product. So let's leap straight in with the definition. Okay, so the dot product. So we take two vectors, either in 2 space or 3 space. So let's just look at definition part 1. So we take the vector u, which is u1, u2, v, v1, v2. The dot product of u and v, denoted by the u and the v with a dot between them, is given by this. It's u1 v1 plus u2 v2. So we multiply the first two entries of each vector and then add when we multiply the first two vectors, second two vectors of entries of the vectors. And then similarly for 3D, if we have u dot v, it's u1 v1, u2 v2, u3 v3. Something really important to notice here, we're starting with two vectors and we're taking this dot product, but the answer, what we get out of it, is a scalar. It's just a number. Okay, so we mentioned in the previous video that we can't really multiply vectors, but this looks a little bit like it. But as I say, we have to be careful. We're not expecting a vector as the output. We get a number as the output. Okay, so let's go ahead and just do a couple of examples. So for u and v, 3, 1 and negative 2, 5. If we want to take the dot product of them, so we indicate it with that dot there. So basically we just take the 3 times negative 2, 1 times by 5, so we get negative 6 plus 5, that's negative 1. And as I mentioned previously, that's a scalar, a number answer. Do exactly the same in 3D in R3. Take each of the elements, so we take the 2 times by the 2, plus the 1 times the negative 3, plus the negative 5 times by 0. Add it all up, we get 4 minus 3. The last term is, of course, 0. So we get 4 minus 3, which is 1. Again, a scalar. Just some properties, fairly straightforward. We have commutative property again, so u dot v is the same as v dot u. It doesn't matter which order we do it in. We can distribute that u. So u dot v plus w is u dot v plus u dot w. We can also distribute a scalar anywhere we wish, so we can take the dot product first to multiply. We can multiply the scalar by either the u or the v. Number 4 says if you take the dot product of the 0 vector with any other vector, you'll get the scalar 0. And then finally 5 says if you take the dot product of something with itself, it's the magnitude squared. And thinking back to how we found that magnitude, that hopefully makes sense. Okay, and then, well, so why? Who cares? So one interesting point about this is that we can use this dot product to find angles. Okay, so we take u dot v. We've seen previously how we would actually calculate that, but it has another value which is given by this. So it's the magnitude of u times the magnitude of v times the cosine of the angle between them. Okay, that theta is the angle between them. We take that theta between 0 and pi. That just obviously depends how we take the arc cosine, but we assume it's that default value between 0 and pi. And so just taking that formula and rewriting it, basically solving for theta, we get the inverse cosine of u dot v divided by the magnitude of u, magnitude of v. We take all that and take the arc cosine, we get that angle. Okay, so let's go ahead and do that. And before we do that, actually, let's just look. So if u dot v is greater than 0, then the angle is less than 90 degrees, less than pi over 2. If the dot product is 0, then the angle is indeed pi over 2. That's a right angle. And if the dot product is less than 0, we get an angle between pi over 2 and pi. And so in particularly that middle one where the dot product is 0 is something of interest that we'll see in just a second. Okay, so let's go ahead and just do it. So let's take two kind of random vectors here, 3, 4, and 5, negative 2, and find the angle between them. Okay, so first off, we take the dot product. Okay, so 3 times 5 and 4 times negative 2, so that's 15 minus 8 is 7. Then we take the two magnitudes, and we're just throwing the formula in on the right-hand side there so we can see it. So the magnitude of u is the square root of 3 squared plus 4 squared, which is 5. Magnitude of v is 5 squared plus negative 2 squared, so 25 plus 4 is square root of 29. And say those are all the pieces we need to now throw in that formula we have on the right hand side. We have the 7, the 5, the root 29. So we take the arc cosine of that 7 divided by 5 times by root 29, and we get about 1.38 radians. Okay, we should probably get the angle in radians. Of course, you can find it in degrees, but radians we should be using in calculus. Okay, so that's how we find the angle between two 2D vectors. We'll do the same thing in 3D. We'll go a little quicker now. So we have 1, 2, 3, and 4, negative 1, 2. We find the dot product by taking each term. Find the two magnitudes, which are root 14 for the first one and root 21 for the second one. And then we divide that 8 by that root 14, root 21, take the arc cosine, and sure enough, that gives the angle. Okay, so we went through that second one a bit quicker, but it's all exactly the same as it would be for 2D. And then let's leap into a definition now. So two non-zero vectors u and v are orthogonal if their dot product is 0. Okay, when we say orthogonal, if you want to think perpendicular, that's certainly a reasonable way to think, because the point being that if you're taking the arc cosine and get theta, well, the arc cosine of 0 is pi over 2, or if you prefer, cosine of pi over 2 is 0. So that means if we get that dot product being 0, then we get the angle to be pi over 2. Okay, so again, let's take a simple 2D example. So if we have u is 2, 1, and v is negative 1, 2. The dot product of those two vectors is 0, therefore they are orthogonal. Okay, they are perpendicular to each other. Similarly, if we do it in 3D, we take 1, 2, negative 1, and 2, negative 1, 0. Again, there the dot product is 0, and so the vectors are orthogonal. Okay, again, just taking that dot product shows that. A reasonable question we might want to ask here, actually, before we go on to that, this is to two orthogonal vectors. It's always hard in 3D if you draw these to actually show that that is a right angle, but that is indeed a right angle between those two vectors. But say it's a little hard to see in the 3D space. Okay, so suppose we ask the question, well, give me two vectors that are orthogonal. So 2, negative 3, 4. Okay, thinking in 3D, if you think about a vector in 3D, there are actually infinitely many different vectors we could have that are orthogonal to that. And this is just asking us to find two. Well, there's a couple of approaches to this. One is, well, let's just pick the first two values to be whatever you want. Okay, so pick the first values to be 1 and 1, because that's nice and simple. And then we're just going to pick the third one to be x and make that x work, right? Let's pick that x or calculate that x to be the thing that makes the dot product 0. So we take the dot product of the 2, negative 3, 4, and the 1, 1x. Then we get 2 minus 3 plus 4x equals 0. So we get minus 1 plus 4x equals 0, which gives us x equals a quarter. So our orthogonal vector would be 1, 1, a quarter. There's one other approach. There are multiple approaches. One other approach is we'll just make the last entry 0 and just take the negative and switch the order of the first two. So the first two values in our original vector were 2 and negative 3. So we change the order to give ourselves 3 and 2 and take the one that was negative and make it positive. And hopefully you can see there, I get 3 times by 2, which is 6, but then 3 times negative 2, which is negative 6. Add those together, we get 0, and then that last term is also 0, so that's enough. Okay, so we've covered a lot today, and what we're going to look at now is orthogonal projections, and in particular how we use dot product to find them. So when we say orthogonal projections, we've got the vector u here and the vector v, and the question we're going to ask is how much of u goes along v? Okay, how much of u is in the direction of v? And that little right angle there indicates that, right? It says, well, how much of that u is going along, so where does it hit that right angle? Putting it in more of kind of vector terms, if we take the vector u and think about it going along v, well, w goes along v and z is perpendicular to v. So we can break u apart into the piece that's along v and the piece that's perpendicular to v, which would be w and z. But in particular, for right now, we're interested in the orthogonal bit. So in other words, how would we calculate w? okay, the bit that goes along it. We'll leave straight to the formula, but it really all just comes from like the part that's parallel to v. So we have non-zero vectors u and v, the orthogonal projection of u onto v, which we denote with this proj, and then we have the subscript of the v, and then the u is given by that. So just working through this formula a little bit. So the numerator there is u dot v, that's a scalar. The denominator is v dot with itself, which is also a scalar, so that whole fraction is a scalar. And then we multiply it by v, and that should make sense because it's in the direction of v. Okay, it's just a certain distance in the direction of v, so we should multiply it by v to get the direction at the end. So we get the constants, the u dot v, the v dot v, and multiply by that direction v vector. So this is a vector, right, which again is what it should be, right? W goes along v in that direction. Okay, so having said all that, and actually once we have the formula, this really isn't that bad. We would have u and v, and we want the projection of u along v. The formula will give right there. So we have to calculate each of these pieces. Well, u dot v is -1. And you know, just how we find that. So we take the 2 times by the 1 times the -1, and the -1 times the 2, add them all together, get -1. Then we take the v dot with itself, and really that just entails squaring each entry, right? We're timesing each entry by itself, so it's 1 squared, -1 squared, 2 squared. So those are all our pieces, and really that's about it. Because then when we plug that all in, we put the vector v that we have at the end there. So we get -1/6 times by the vector 1, -1, 2, which is a vector in itself in that direction. So I'll say that's the projection of u onto v. It's the amount of u that goes along in the direction of v, I suppose. Okay, and that's all we have on the dot product. Thank you.